Good morning. This is Dr. R.K.Arya, Associate Professor in Department of Chemical Engineering, IIT Jalandhar. Today I am going to explain heat generation in solids. So these are some typical cases where the heat may be generated. So the absorption of radiation throughout the volume of a semi-transparent medium such as water can also be considered as heat generation within the solid medium. Nuclear fuel rod is considered as a heat generation within the solid. Electrical resistance wire is also considered as a heat generation source. Chemical reactions also considered as the source of heat generation because they also generate the energy. Now in case of electrical wire, E dot generation means energy generated per unit time, per unit volume. So this is E dot, so I square Re, the resistance of the wire, divided by pi R naught square L. So now we are considering, let us solid medium of surface area A, As, volume V, and constant thermal conductivity, where heat is generated as a constant rate of E dot generation per unit volume. Now this is the case here. The heat is transferred from the solid to the surroundings at T infinity with a constant heat transfer coefficient H. All the surfaces of the solid are maintained at a constant temperature Ts. Under steady state conditions, so whatever heat is being generated within the material, so E dot generation would be equal to the energy generated per unit volume multiplied by volume, and this E dot generation totally would be lost to the surroundings. So whatever heat is transferred from the solid, that is the rate of energy generated within the solid, and the surroundings are maintained at temperature T infinity, heat transfer coefficient H, and the surface temperature of the solid is Ts. So we are balancing that Q dot equal to E dot generation into volume. At the same time, we are neglecting the radiations. From Newton's law of cooling, we can write Q dot equal to HAS Ts minus T infinity. So Q dot is E dot generation into V. Can substitute here. So from here we can get the expression of Ts, the surface temperature of any solid. So T infinity plus E dot generation into B divided by H into A. Now this is general expression is applicable for rectilinear figures, cylindrical figures, and spheres. So in case of large plane wall of thickness 2L, area of the surface is 2AL. So this side area is A, this side also A, so total area is 2A. From here the heat is being lost. Volume would be 2L, that is the length of the wall, and multiplied by area is volume. In case of long cylinder of radius R0, so in case of cylinder, surface area is 2 pi R0 L, volume would be pi R0 square L. In case of the sphere of radius R0, surface area is 4 pi R0 square, volume is 4 by 3 pi R0 cube. So by putting all these expression for surface area and volume, we'll get the expression for T surface for plane wall is T infinity plus E dot generation L upon H. In case of cylinder, T infinity E dot generation R0 upon 2H. In case of surface of the sphere, T infinity E dot generation R0 upon 3H. So as you will see from here that this surface temperature is keep on decreasing as we are going from plane wall to the sphere, and for time being, if you are considering, let's say, L length of the wall is same as the radius of the sphere of the cylinder, so you say this is this. In case of wall to cylinder, this has become half, and in case of wall to sphere, it has become 1/3. So your surface temperature will keep on decreasing. Now heat transfer from a solid cylinder with the heat generation under steady state. So entire heat generation within the medium would be the heat conducted through the outer surface of the cylinder. So in that case, let's say this is the cylinder. So you are generating energy, E dot generation into volume. You have volume is VR of radius R. Surface area for this corresponding is this AR is 2 pi R dr, and then Q dot is E dot generation. So under steady state operations, for in case of cylindrical coordinate, your governing equation is minus K AR dt upon dr equal to E dot generation into VR. So AR is 2 pi RL, and this VR is pi R square L. So if you substitute that here, K 2 pi RL dt upon dr E dot generation pi R square L. So dt is minus E dot generation upon 2K R into dr. Integrate that. So if you integrate that, you will get Ts minus T0 equal to E dot generation upon 2K R square upon 2. So this can be taken as delta max equal to E dot generation upon 4K upon R into R naught per square. So T naught is the center line temperature of the cylinder, which is maximum. Now T center would be equal to T naught equal to Ts plus delta T max. So T surface plus E dot generation R naught square upon 4K. This is center line temperature for the cylinder. Now in case of plane wall, so for plane wall, the governing equation is minus Ka dt upon dx equal to E dot generation into Vx, the volume. So for that case, you have Ax is a wall dt upon dx E dot generation into a wall. So Vx is actually volume. So volume is x into a wall. So from here dt is minus E dot generation upon k x into dx. So now you can integrate that. So by substituting here, integrating that, you will get T naught equal to Ts plus E dot generation L square upon 2K, and from here the delta T max is E dot generation L square upon 2K. In case of a sphere, we can have again the governing equation is minus K AR dt upon dr E dot generation to VR under steady state operations, purely in radius heat transfer. So here you have minus K 4 pi square dt upon dr equal to E dot generation 4 by 3 pi r cube. So by integrating that, you will get this Ts minus T naught equal to E dot generation R naught square upon 6K. So delta T max for sphere is E dot generation R naught square upon 6K. So in this we have found the center line temperature, maximum temperature, and surface temperature in case of energy generation of within any solid. Could be a plane wall, could be a cylinder, and could be a sphere. So these are the references from Sengel, heat and mass transfer and heat and mass transfer fundamental approach. Fundamental and application, one is practical approach actually. So thank you very much. In case of comment, you can drop your comment there. Thank you.